Hey everybody, Mike here. In this video, I'm going to dive deeper into the debug ports I exposed for my Starlink Dish teardown, including the full Bootup log and Linux serial login of this Starlink Dish. Coming up. My original plan for part 2 of this teardown was to go through this metal plate, pull it off, and expose what's underneath. But since publishing my part 1, there's been another excellent teardown by Keiter. So instead of pulling this off and wrecking another Starlink dish, because it is a pretty destructive process, he's given me permission to show highlights from his video, so you can take a look at the highlights. And then I'm going to concentrate on this debug port that was exposed from my first teardown. So here are the highlights.
Yeah, I have sacrificed Starlink's dish, also known as Dishy, to the teardown god so that you can be the first to see what's inside and get an idea of how it works. This is not designed to be disassembled. Now, there is in fact a tremendous amount of adhesive on the bottom of this. In fact, there's what appears to be a VHB, a 3M VHB-like adhesive, very high bond adhesive that lines each of these ribs. This is the front of the Dishy phased array assembly. Now, this is the sky-facing side. So what you're seeing here are the individual patch antennas that are responsible for forming the phased array. So each one of these elements is an individual, or is part of a couple of elements that comprise a single antenna that's capable of transmitting and receiving signals. This is the back of the phased array assembly. These connectors are the ones that I referenced earlier. These are the ones that are exposed through the shield on the back. Next, over to the right here, or clockwise, you have the PoE, Power over Ethernet magnetics. So a set of transformers that are used for the Power over Ethernet functionality. And then you have the power supply. Continuing counterclockwise, what we see is the application processor and its related components. So this is the application processor. This is the brains. This runs the SpaceLink's primary software package. It has 2 RAM chips that are associated with it, and it also has an eMMC flash storage device which contains Dishy's file system. And I'll go into detail about those a little bit later. But as we continue clockwise, we see that we have a little bit of another power supply. As we continue counterclockwise, we see a little area that's actually designated GPS, and this contains a GPS receiver chip, and I'll dig into that a little bit more, as well as a 2 megabyte flash. We see some more power supplies around the outside here. And really that's it on the tour of the outer edge. So what I've noticed overall is that there are these blocks that are comprised of kind of these 8 smaller ICs, all of which are the same part number, as well as this larger IC here. I suspect that essentially each one of these blocks operates as a component of the overall phase shifting array, and basically, we're able to form the beam by having the application processor address each of these individual design blocks. It's fair to assume likely that the 79 of these design blocks, so a total of 632 of these ICs, and presumably 632 elements on the front of the board, I would assume that each of those elements can be individually driven and may be able to operate as both transmit and receive in some capacity. So
wow, so it's really an amazing amount of technology packed into this. That teardown does answer a few questions I had. Is there a real GPS receiver in here? Which there is, to find the dish's location, and a few other things I'll follow up on in later videos. It's great as well to see Ken collaborating with other YouTubers. So he's sending the internals of the board to the signal path to do a further analysis of the RF components. And he's even offered to send me the white backplate for Starlink from his teardown, because mine has a bit of a hole in it from my last video. So with the board level investigation being looked into by the signal path, I'm turning my focus to the debug port I exposed from my last teardown. I crossed a big milestone as well since my last video, 10,000 subscribers. So I just want to thank all of you for subscribing, for clicking that like button, for commenting, and really just joining me on my journey. Now, YouTube doesn't send out a plaque for 10,000 subscribers, so I figure I'll make my own with this spade bit that's caused so many comments about people recommending better ways of drilling holes through expensive electronics. So thank you again to all of you, and here's to many more videos. So let's take a look at that port. Okay, so if you remember from part 1 of the teardown, this debug port looked like this, just an unpopulated pad. So what I've done since then is initially I just soldered a small lead onto the ground pin, and that was just to allow me to attach the ground lead of my oscilloscope probe. And then I used the tip to just probe around various points, trying to find which signals were interesting. As you can see from this video, I was a little bit impatient in a rush and I peeled up one of the traces slightly. And that kind of gave me a bit of pause. These dishes are in short supply, so I didn't want to damage one. So I stopped really there, and what I went to next is getting a connector, and you can see this one on here. I wanted to solder on a connector so that all my future work could be on another board and I wouldn't risk damaging the Dishy board. So that's part of the reason why there was so much time between the last video and this video, just lead time for this and a few other parts. But you can see here what we've got is it's a 20 pin connector, 2 rows, and it's 0.5 millimeter, 0.5 millimeter pitch for these connectors. So it's pretty fine, definitely a lot smaller than the motor controller and the Ethernet connector. So I soldered that on, and now all my further work is with the mating connector, where I can just solder onto that. And the mating connector only costs about 60 cents. So I'm a lot more confident buying a handful of those, and if I screw them up, no big deal. I can just unplug it and plug on a new one. Eventually, as I figure out what all the pins do, I'll probably make my own circuit board to mate directly on here. But for now, I'm just prototyping things by soldering directly onto the connector. So let's take a look now at how those signals look, and you can see what the serial port signals look like. All right, so what I've got here is the mating connector, and that's just there, and it's pretty tiny, the same 0.5 millimeter pitch. And I've just soldered on, pretty rough solder, onto the 3 pins I'm interested: ground, transmit, and receive, which maps through to the same pins that were exposed on the side. So all the interesting pins are also on this 20 pin connector. And then these fine wires I just brought to a small breakout board here, and then just soldered on some thicker wires that will plug into the bridge board, which are just bare right now. So that's really all to expose the 3 serial pins, TX, RX, and ground, that are visible on the board here. So I can just plug that into my soldered on connector. Just being gentle. And that gives me a pretty reliable connection to the ground. And you can see I soldered a bit of a loop in the wire for me to attach my oscilloscope to. And then the TX and RX pins. And then my scope just plugs onto those pins. Okay, so let's take a look at the signal we're actually getting. All right, this scope is a Tektronix MSO, mixed signal oscilloscope. I've had this for years and I love it. It's got analog inputs, in this case 4, plus a digital input for up to 16 digital inputs. So when I'm first starting with a new signal, I can start with the analog input to get a good idea of what that is. And I like to start by setting the trigger into an untriggered roll, so the signal is just running across the bottom. And then I also adjust my scale so that I'm viewing a large time frame. And you can see it slowly scrolling across. So what I'm going to do now is actually power on Dishy, and I'm connected to the TX port. So this should be whatever Dishy is sending out to the world, and I should see some blips on this line. So it's just going to scroll past, but let's take a look. So you see it's idle high and then lots of activity here. I'll grab some screenshots as well as we go. Another nice thing about the scope is it can capture screenshots to this USB stick, and I'll put those on the screen for you to see. Okay, so first highlight, I'm going to pop on my cursors. You can see here that at the cursor point, if I just stop the scope, 1.8 volts. So that's 1.8 volt logic for Dishy's serial port here. So I'm going to start this back up again, and I'm going to turn off Dishy before it starts moving around the antenna mount. So we've already learned a lot. It's 1.8 volt logic and idle high and lots of activity as it goes. So I'm going to turn the cursors off and now go back to my trigger menu. I've already got this set. I'm going to change my source to trigger on the signal I've got. I'm going to use a falling edge, and I'm going to set my level. You see I've already got it here at 1.2 volts. And then I'm going to change the mode instead of untriggered roll. I'm just going to set it to normal and then clear off the menus. So it's running now, and it's just waiting for a trigger. So a trigger is when my signal drops from high to low. This is going to stop it right at this trigger point here. So the idea is I'm going to be able to capture my signal and freeze it in time to do some analysis. So here we go. I'm going to turn the user terminal back on again, and we'll see what we capture. Okay, so you can see it capturing a few different times as the serial port receives signals. So what I'm going to do now is zoom in and try to capture a bit more detail. So this is zoomed in, so you see there's a lot of kind of sampling aliasing going here. It looks really rounded off. But what I'll do now is I will restart the user terminal again, and we'll see now that we're zoomed in, the captured signal will be a lot sharper, a nice square like you'd expect. So that's terminal off and now back on again. So there you can see some nice square waves. And what I'm going to do is I'm just going to ask for a single capture. So there we go. It just locked on once. It's now stopped. So that screen capture is going to stay there. And I'm just going to turn the user terminal off, but you can see my waveform is captured. So this is the serial signal coming from Dishy, the user terminal. And there's a few different things I could do here. What I want to do is actually figure out the baud rate so that I can figure out how to receive this in my computer. There's a few different ways we can do that. We can zoom in and use the cursors to measure. So you can see here, I've got my two cursors, and I can use these controls to try to capture one bit here. So that's the start, and then I'm going to move the end over. You can see that second cursor line coming in. If I get that just so, then I can keep zooming in to get more detail here. So this is measuring the duration of one time interval here. And you can see it's around 8.7 microseconds. So that's the width of one bit. And you can do the math and figure out what that is in baud rate, bits per second. But a great thing about this scope, the MSO, is it's got built-in decoding modules. So I actually have, as part of my scope, this serial decoder for RS-232 structured signals. So you see here, I can actually turn on a bus B1 here. And then I've got these separate lines, and I've actually already labeled mine as dish, and you can see it can support up to 2 signals, send and receive. And you'll see here for these, the signal you're seeing on input 1. If I go to my define inputs, you can see here my RX is input 1, And what I'm going to do is change my speed until it can actually decode a signal. So here's my bit rate, and I'm just going to turn that up. And you'll see things like this where it has an error and then it decodes something. I'm going to keep changing this until I get a decoded signal without an error. So that red box is a framing error. And what you'll see is once we get the right baud rate, you'll see the signal without those framing errors. There we go. So 115.2 kilobits per second, 8 data bits, no parity. And you can see here, we've got the decoded signal in hex. So now we know the baud rate, and the last thing I'm going to do is change it, instead of displaying in hex, let's look at it in ASCII. Now this was just kind of from the middle of a communication. So what I'm going to do now is set this up so that I'm zoomed in to an amount where I can still read the characters. I'm going to clear this off. And now we're going to run it again to do a single capture. And then I'm going to start up Dishy and we'll get the very first bytes that it sends out. So single capture. And now it's waiting for the trigger. And now I turn it on. And boom, there's that first capture. So it captured the very first bytes and then paused. So now that it's done the capture, and I'll just take a screenshot here. Now I can zoom in and you can see we get a better look at this decoding. And I'm just going to save a few screenshots for you. But now that it's zoomed in, we can actually scroll through with the horizontal position. And you can see this is the text Dishy's sending out. Info, auto startup, MO, and that's the end of our capture window. So that's a really cool feature of this scope. I love that for investigating a new signal. So from that, we know the voltage, 1.8 volt. We know the baud rate, and we know the parameters, the no parity bits, one stop in. So with that, now we can actually connect this up to a computer and get the full serial port console. All right, so what you're looking at here is a USB to serial converter. This is a development board based on the FTDI FT232R chip. So this is a great little interface adapter, and I chose this one because it has an easy way of supplying a separate logic voltage. So it was very easy to change this to be a 1.8 volt logic signal to and from Dishy. And over here, that's what you're seeing here is just a small linear regulator to convert the 3.3 volts from the USB bus into the 1.8 volts that it wants to send to the user terminal. So with that connected up, once I plug that into my computer, it'll just show up like a normal serial port, and I'll be able to connect at the right baud rate, and it will convert it to the 1.8 volt serial logic I need to actually communicate with the user terminal. Okay, now the moment you've all been waiting for. Here's the boot up, and you're viewing the serial console. And there is the SpaceX user terminal login prompt. Pretty slick. And if I just try the basic, root, you'll see not correct. So I've captured a few of these complete boot up screens. You can see those on my GitHub page, linked down below. Immediately what jumped out is these hash values, which seems to be the hash of the actual kernel image and the RAM disk. So I really wanted to know if they were going to change if I actually connected my dish to the Starlink constellation, if it would be effectively doing an update. And after all this experimentation and soldering and poking and prodding, I really kind of wanted to know if the dish was still going to work. So I took it outside and set it up. And as you can see, it's seeking and seems to be orienting itself. And if I do my speed tests, finally, I know everyone's been asking about the speed tests. Here you go, fully functioning Starlink Dish, just not quite as waterproof as it used to be. And then I did one more boot just to see if things were the same. And you can see the comparison again on the GitHub page, but either I didn't leave it on long enough, or maybe they're just not doing updates, but it's exactly the same. A couple highlights from the log message as I scroll by, you can see they're using U-Boot, which is a very common bootloader for embedded systems. Great little Starlink ASCII art there in the user terminal. Is production hardware? Yes. Type Falcon to stop boot process. Definitely something to look further into there. Loading the kernel. And you can see right there, it's a Linux OS. ARM64 architecture. The device tree is a Rev 1 pre-production board version. And then right at the bottom, development login enabled, no. Definitely an area of exploration to try to get that to change to yes and see what happens. Let me know in the comments down below if you have any guesses for the username and password. I'm going to try them all out and I'll let you know the results. As always, subscribe if you want to get updates. Click the bell icon to get notified as soon as I post my new videos. Thank you everyone for watching. See you next time.